In this video, we'll talk about combinatorics, aka counting. The big idea is this. In calculating the probability of an event, we often need to count up the number of possible outcomes in that event. But counting isn't always easy. We need some combinatorial tools to help. In this video, we'll discuss 3 different tools: the multiplication rule, permutations, and combinations. Let's begin with the multiplication rule. Consider an example. If Kai has 2 pairs of pants and 4 shirts, how many outfits can they make? To answer this question, we can start by drawing a diagram. First, suppose Kai picks out a pair of pants, for which they have 2 options. And after picking out a pair of pants, they pick out one of 4 shirts. In total, then, they can make 8 different outfits. They can wear pants 1 with shirts 1 through 4, or pants 2 with shirts 1 through 4. Though this example is small enough that we're able to draw and use this diagram for counting purposes, this won't always be the case. Instead, we can use the multiplication rule. To this end, we first notice that our problem combines 2 separate operations. Kai has to pick a pair of pants and pick a shirt. We then note that there are 2 ways to perform the first operation. They have 2 pairs of pants, and 4 ways to perform the second operation. There are 4 shirts. When we multiply these, we get the total number of ways to perform these 2 operations. We can make 8 total outfits. Consider a second example. Suppose that Kai, Alicia, and Jenna each order a smoothie, and each must choose one of 4 types of smoothie: apple, beet, celery, or dragon fruit. In determining how many possible orders they can make, notice that we have to combine 3 operations: Kai's order, Alicia's order, and Jenna's order. Each of these operations can be performed in 4 different ways. There are 4 different types of smoothies. Thus, in total, these 3 friends can make 64 different orders. Among these 64 orders, it's important to note a couple of properties. First, the order of operations is important. For example, the outcome ABC is different than BAC. Mainly, Kai having apple and Alicia having banana is different than Kai having banana and Alicia having apple. Second, we're sampling from the possible outcomes for each operation with replacement. For example, it's possible that Kai, Alicia, and Jenna all order an apple smoothie. We might observe an outcome AAA. In general, these examples have established the multiplication rule. The framework is as follows. The scenario of interest can be broken down into K operations, A1, A2, on up to AK. Each operation AI can be performed in NI ways, where NI might differ by operation. For example, in making an outfit, we had 4 shirts but only 2 pants. Next, as we saw with the smoothie example, the order of operations is important, and there can be repetition from operation to operation. That is, we're sampling with replacement. Then, under this framework, to count up the total number of possible outcomes for the collection of operations, we can multiply the number of ways in which each can be performed. Hence, multiplication rule. Consider a next example that will help us think through our next combinatorial tool, permutations. How many 4-letter words or permutations can we make from the letters A, B, C, and D? If we take the time to write these all out, we can come up with 24 possible words. The first row here shows the words that start with A, the second row shows the words that start with B, and so on. Notice 2 important properties here. First, the order of the letters is important. For example, ABCD and DCBA are different words. Second, we're sampling without replacement. For example, no word can have more than 1 A in it. Again, this is a pretty small example, so we shouldn't rely on being able to write out all possibilities. Instead, we can use a combinatorial tool. In this case, we can apply or appeal a special case of the multiplication rule. Mainly, notice that writing out a 4-letter word consists of performing 4 operations. We pick the first letter, then the second letter, then the third letter, then finally the fourth letter. For the first letter, we can pick any one of the 4 letters, A, B, C, or D. However, remember that we can only use each letter one time. Thus, after we use up the first option, or one option for the first letter of our word, there are only 3 options for the second letter. Subsequently, there are only 2 options for the third letter and 1 option for the last letter. In total, there are then 4 factorial, or 24 different words that we can make from our 4 letters. Next, suppose that instead of using all 4 letters, we only want to make 2-letter words, using the letters A, B, C, and D. In this case, there are only 12 options. Instead of writing these out, we can again appeal to the fact that writing a 2-letter word consists of 2 operations. There are 4 ways to pick the first letter, and 3 ways to pick the second letter, or in total, there are 12 possible 2-letter words. When the numbers we're working with get even bigger, we can also take the following shortcut. The total number of 2-letter words that we can make from 4 letters is 4 factorial over 2 factorial, or 24 divided by 2. We can observe here that this calculation does indeed give us the right answer, 12. But let's consider why this works. First, notice that in the numerator, we're counting up the total number of words that we can make from all 4 letters. But remember that we only care about 2-letter words, hence the first 2 letters of the words here. Notice, however, that some of these words are double counted. For example, ABCD and ABDC start with the same 2 letters, and we don't care about the last 2 letters. To get rid of these, we can count up how many ways that we can rearrange the 4 minus 2 letters that we don't want to use in our final word. Here that number is 2. We can rearrange the last 2 letters C and D as CD or DC and still get the same 2-letter word, AB. Dividing by this factor then removes the double counts. And focusing just on the first 2 letters again gives us our 12 official words. In general, these examples have established how to count up permutations. The framework is as follows. Suppose there are n distinct objects and we want to create a sequence of k of these objects, where k can be 1, 2, on up to n. Next, as we saw in our example, the order of objects in the sequence is important, and no object can be used more than once in the sequence. That is, we're sampling without replacement. Then under this framework, there are n factorial ways to permute or create a sequence of all n objects. Further, the number of ways to permute k less than n objects is n minus 1, n minus 2, down to n minus k plus 1, or n factorial divided by n minus k factorial. Finally, consider our third combinatorial tool, combinations. For example, suppose 4 people, A, B, C, and D, volunteer for a 2-person committee. How many different committees can we make? Writing out the options, there are 6 possibilities, and these reflect 2 important properties. First, in constructing the committees, order is not important. For example, A, B, and BA both have people A and B, thus they're the same committee. Second, we're sampling without replacement. We can't have a committee of the same person. For example, BB isn't an option here. As usual, we shouldn't rely on being able to write out all possibilities. Instead, a combinatorial shortcut to count up the number of 2 object groupings that we can make from 4 total objects is 4 choose 2. Specifically, or by definition, this combination is calculated by 4 factorial divided by 2 factorial, where 2 is the number of people we're selecting, and 4 minus 2 factorial, where 4 minus 2 is the number of people we're not selecting. Plugging in the numbers, this again gives us an answer of 6 possible outcomes. But let's explore why this works. First, the numerator counts up the total number of ways that we might arrange the 4 candidates. But we only want committees with 2 people, thus we'll focus on just the first 2 letters. Further, we want to eliminate some of these options here, some of these 24 options. For example, remember that order isn't important. Thus, AB and BA are the same committee. Thus, these 2 options are the same committee. In general, there are 2 factorial, or 2 ways, that we can arrange the 2 people on the committee and still get back the same committee. Dividing by this number then accounts for the fact that order isn't important. But we still have too many options left. We're still double counting some committees. For example, ABCD and ABDC start with the same 2 letters, and we don't care about the last 2 letters. To get rid of these, we can count up how many ways that we can rearrange the 4 minus 2 letters that we don't want to use in our final word. Here that number is 2. We can rearrange the last 2 letters C and D as CD or DC. Dividing by this factor eliminates the double counts. And focusing just on the first 2 letters again gives us our 6 official words. Consider a bigger example. Suppose we wanted to pick 3 of 100 people to win a free concert ticket. Then how many different combinations of concert goers could we get? Again, the order of this combination isn't important, and we can't choose the same person more than once. Thus, we can calculate this by 100 choose 3, or 100 factorial divided by 3 factorial, and 100 minus 3 factorial. In this solution, we start by counting up the total number of ways to arrange all 100 people. Then, recognizing that the order of the people isn't important, we divide by the number of ways to arrange the 3 winners and still get the same outcome. And finally, recognizing that we only care about the first 3 people in the sequences, we divide the number of ways to arrange the 97 non-winners and still get the same 3-winner outcome. Finally, we can plug in some numbers. We can write out 100 factorial in the numerator, and 3 factorial and 97 factorial in the denominator. Now these factorials are pretty large, thus they might trip up our calculators or computers. If so, we can simplify the calculation by noticing the terms that cancel out of the numerator and denominator. We're then left with 100 times 99 times 98 divided by 3 times 2 times 1. In total, then, there are 161,700 different ways that we can pick 3 of 100 people to win a concert ticket. Definitely too many options to write out and count by hand. In general, these examples have established how to count up combinations. The framework is as follows. Suppose there are n distinct objects and we want to choose k of these objects without replacement. Further, the order of the objects in the final selection is not important. Then under this framework, there are n choose k ways to randomly sample k from n objects, where again, n choose k is calculated by n factorial over k factorial times n minus k factorial. In conclusion, the slide here outlines the 3 combinatorial tools that we've explored in this video. The appropriate tool for the job depends upon whether the order of outcomes is important, and whether repetition or sampling with replacement is okay in the outcomes.